Welcome all of you to my this live session lectures. Okay, today we'll discuss about the geometrical interpretations of eigenvalue and eigenvectors. Okay, this is my tutorial 11th. Tutorial 11. Aim of this lecture is to present the geometrical interpretations of eigenvalue and eigenvector. So can you please tell me what is the geometrical interpretation of eigenvalue and eigenvector? Yeah, please someone try. Yeah, try to give the answers. What is the geometrical interpretations of eigenvalue and eigenvectors? Ravi, Rajesh,
Yes,
yeah,
sir.
try to give the answers. What is the geometrical interpretations of eigenvalue and eigenvector? What is that? Please tell me. What is the eigenvalue and eigenvector of a matrix or a linear map?
Sir, solution there, no?
What is the eigenvalue and eigenvector?
The solution of the characteristic equation of our matrix.
Yeah, I agree. So before going to the characteristic polynomial or characteristic equations, can you give the normal definitions of eigenvalue and eigenvector? Basically, my aim is to tell you the geometrical interpretations of eigenvalue and eigenvector. Everyone know about eigenvalue and eigenvector, how we can find the eigenvalue, okay, and what is the property, everyone know, but can you tell me what is the geometrical interpretations of eigenvalue and eigenvector and what is the uses of this? Suppose take R2, okay, this is your R2 plane, okay, take a operator A, okay, take one non-zero U. So take the line passing through origin and U, okay, this is your line passing through origin, okay, this is generated by U, okay, is it fine? Generated by U means alpha time U, where alpha is belongs to your field, okay. So if A acts on U, okay, when A acts on U, this vector might be here, might be here, might be here, here, or here, or here, we don't know, okay. So after acting A on U, okay, this U vector can be shifted to any place on R2, okay. So there is some possibility that after acting A on U, U lies on this line. Yeah, there is some possibilities there, is it or not?
Yes, sir, it might happen.
Yeah, might happen. So up if one linear map or one matrix act on some vector, after acting on that vector might be lie on the line passing through the origin and that point, okay. So that time this is your that is the line, this line generated by you, it's defined like that, okay, everyone are known about that. So we can write it as, suppose after acting on you, okay, suppose it is on that line, so we can write it as lambda into u. It's fine. Suppose that if after acting on u, okay, if this point is line on that line, that time we can write au as a lambda into u, where lambda is a from real r. Are you agree with me? If this possible, then we can write. It's fine or not? Please tell me.
Yes, sir. Fine, sir.
Yeah. So can you give me what is the geometrically I am trying to say? And what is this vector? What is the mean of this vector? This mean of this vector means after when we are acting with linear map A on U, okay, if suppose this vectors is belongs to this line, okay, that time this lambda means that this vector is stretched by that scaling. This is the scale vector or stretch vector, whatever you can want tell. Okay, so it is scaling means it is proportional to this u. It might be less than this length lambda into u, might be less than of your previous u, or might be greater than or equal, we don't know, but this is the proportionals of u. So this is stretching. Okay, after when a acts on u, and it's suppose it's light on this line, that time it's might be increase or decrease with your magnitude. Okay, so this vector is called an eigenvalue. Okay, and if u is non-zero, that time we'll call it an eigenvector. Okay, it's fine. It's fine or not? Please tell me.
Yes, sir. Fine, sir.
Yeah, so I am writing here, you can note it.
So what you told about eigenvector in the end?
Yeah, I am writing, please. Yeah, follow it. It will be better for you, I think. Geometrically, what we can say, geometrically, okay, and eigenvector corresponding to a real non-zero eigenvalue, okay, points in which direction or in direction, okay, in which it is stretch. Okay, understood this one. If you suppose this lambda is non-zero, if zero then that time any vector if you multiply, it's no matter, that time direction is will not be any issue. Okay, yeah, if lambda is zero, that time, yeah, direction is not a matter. Okay, but if lambda is a non-zero means eigenvalue is a non-zero, then geometrical eigenvector corresponding to a non-zero real eigenvalue, okay, points in direction or in which direction it is stretch. Okay, if it's it can be stretch in positive direction, it might be can be a stretch in negative direction. When it's stretch in negative direction, that time we'll get the negative eigenvalue. When it is stretch in positive direction, we'll get the positive eigenvalue. Okay, it's fine.
Yes, sir.
Understood everybody? Ravi,
Yes, sir.
what about Ravi?
Yes, sir. Good, sir.
Okay, good. So geometrically an eigenvector corresponding to real non-zero eigenvalue, okay, points in direction in which it is stretched by the transformations. Okay, transformations. Okay, and what is the geometrical meaning of eigenvalue? And the eigenvalue is the factor by which it is stretched. Okay, means what is the scaling? What is the scaling factor? Scaling factor is the eigenvalue, and in which direction it is stretched, this is the eigenvector. Okay, so when we are talking about direction, that time we have to assume that the eigenvalue is non-zero, and every time for every eigenvalue is eigenvector have to be a non-zero. Okay, every time you have to be non-zero. Okay, when we are talking about eigenvalue, if you need the geometric interpretation of eigenvalue, that time, and which direction if you want, that time we need only the eigenvalue is non-zero, otherwise eigenvalue might be zero. Okay, understood?
Yes, sir.
Yeah, so this is the geometric interpretations of eigenvalue and eigenvector is fine, but why you are doing these things? What is the need of eigenvalue eigenvector in mathematics, in linear algebra, you can say, in mathematics? Why it is needed? I'm not going the real life applications, but for as a mathematician, what is the need of eigenvalue and eigenvector? Why you are reading those things, where we are learning those things, eigenvalue and eigenvector of a matrix? What is our aim behind this picture? Could you please tell me what is our aim? Yeah, before giving the answer, I want to note it some definition and some statement. Okay, so this is the definition of eigenvalue and eigenvector. So what is the formal definition of eigenvalue eigenvector? Can you please tell me? This is the geometrical interpretations. This one the geometrical interpretation of eigenvalue eigenvector. So what is the formal definitions of eigenvalue and eigenvector? Please tell me. Yeah, someone try. What is the formal definitions?
So, like if a vector V belongs to a vector space, then linear transformation of V should be equals to lambda times of V. So that lambda is eigenvector value.
Lambda is might be any number, or some restriction is there, or any vector, or some restriction is there on V. Suppose if you take in this picture, if you take u equal to 0, okay, then it will be here. So for every lambda it will be satisfied. If you multiply by any lambda, it will be 0 always time. Okay, but corresponding to a eigenvector, eigenvalue is unique. Okay, it should be unique, otherwise when you'll try to find the eigenvalue eigenvector using your characteristic equation, na? So one characteristic equation, suppose polynomial is degree n, so we'll get at most n roots of a polynomial. Okay, but if you start with 0, every lambda will satisfy. Yeah, so if your u equal to 0, so if you multiply lambda equal to u, so every time we'll get this 0 for all lambda. This is the issue. Okay, so when we're trying to find the eigenvalue eigenvector using the characteristics polynomial na? When we will try to find the eigenvalue using characteristic polynomial, suppose characteristic polynomial degree is n, okay, so we'll get at most n roots. Do you know about this theorem? This is a fundamental theorem of algebra. Did you heard about that?
Yes, sir.
Okay,
Yes,
so,
sir.
so we'll get the at most n lambda. Okay, so if you start with 0, this is the issue. For all lambda it will satisfy. So we'll start with non-zero vector. We'll start with non-zero vector and we'll act a on u and we'll see what is the picture. Okay, it's if it's lies on the line or not. Okay, we will not start with 0. The 0 will be uh, some difficulty will comes. Okay, so we'll start with non-zero eigenvector. So when we'll talk about eigenvector, it's mean every time it's non-zero eigenvector. Okay. So I am writing here formal definitions of eigenvalue and eigenvector. Okay. We say so yeah, I have to mention one. I am talking about only real matrix here. Okay. For for the reason I mentioned the real number, real number, real number. Okay. If you want, you can take the complex. That time, yeah, you don't have to mention this real number. Okay. Why I am talking about real number, you can understand a little bit later. Okay, so my question is, right now I am telling the questions. So for for every matrix eigenvalue exist or not, this is my question. What will be answer?
Sir, please repeat the question for every.
For you have one transformations. Okay, so could you please tell me for every time, for every transformation eigenvalue will be exist, or for every transformations and yeah, you can say like that. For every transformation eigenvalue will be exist or not, this is my questions.
Yes, sir. Not true.
Yeah, need not be true. So for this reason I am talking about real number, real number, real matrix. I'll give you example. Okay, so if you take the complex number na, that time always it will be exist. So I am coming to later. So first please give me time to define the what is the eigenvalue eigenvector. Say real number. Okay, lambda is an eigenvalue of a if there exist non-zero. Okay, where you are taking the non-zero vector, could you understand?
Yes, sir.
Yeah, such that av equal to lambda v. Okay, so this non-zero vector is called as your eigenvector, and this scaling vector, okay, it's called an eigenvalue. Okay, so any non-zero vector, okay, v belongs to your domain sets v. Okay, such that av equal to lambda v is called eigenvectors of a. Okay, corresponding to the eigenvalue lambda. Okay, this is the formal definition of eigenvalue and eigenvector. Okay, so now I want to give you one exercise. Okay, very easy exercise. So before going to giving the exercise, we want to observe something. Okay, so here you observe that suppose u is your eigenvector, then we can write it is as like that. Okay, where u is non-zero and u is an eigenvector of A and lambda is an eigenvalue, or you can tell lambda is a scaling factor of u. Okay, so take another v equal to alpha u, where alpha is belongs to R. Then what we can say about AB? Is this V is a eigenvector of A or not? This is my question. I am taking V equal to alpha into U, where alpha is belongs to your field. What can you say about V? V is a eigenvector of A or not? Please tell me. What we can say about V? I am taking V is a alpha times U, okay, where alpha is from your field. What can you say about V? V is a eigenvector of A or not? This is my question. At first, please tell if U is non-zero, what can I say about V? V will be non-zero, okay, if alpha is non-zero, okay. Okay, now please tell me what we can say about this non-zero vector. Is it eigenvector of A or not?
Sir, eigenvector.
How?
It will be in the direction of u only.
Yes, because we are only scaling the factor by this one, okay, and when we are talking about AB, the scale will be alpha into lambda, this one only, okay. This will be the scaling, okay. Is it fine?
But if alpha is negative, so it will become anti-parallel, no?
If alpha is negative, then it will be sorry.
If alpha will be negative, then it will be in opposite direction of
Yeah,
u.
opposite direction. Yeah, that time your for the reason I have mentioned here. Yeah, for your eigenvector, in which direction? This is your eigenvector. Okay.
Okay, so okay.
Yeah. So this is your direction. Yeah. If you take the negative, if lambda also might be negative. Okay. Then no issue. So here we can observe. So any vector which is a multiple of u is a eigenvector of A. Then what we can say about that? So from here we can observe the generated by u. This is your one dimensional subspace of V, okay, and this is your eigenvector fully, because when we start with the non-zero eigenvector u, so we are getting any vector generated by u is a eigenvector of u. You are agree with me? Any vector generated by u is a eigenvector of. If we start with the eigenvector of u is eigenvector of A, then any vector generated by u is also an eigenvector of A. Is it fine?
Yes, sir.
Yeah. So what we can note? We can note that you can take it as exercise or note. Okay. So if V is an eigenvector with the eigenvalue lambda, okay. If V is an eigenvector with eigenvalue lambda, okay, then alpha into V, okay, is an eigenvector with eigenvalue lambda, okay. In fact, if you consider the sets, okay, in fact the non-empty set, okay, if you consider this set, X belongs to your domain set V such that a x equal to lambda x, okay, is a vector subspace, okay, of V for any lambda belongs to R. Okay, what is the meaning of this non-empty sets? Okay, corresponding every lambda, here lambda is fixed, we are finding that vector x such that a acting on x will be multiple of x, means this x will form a eigen, this x is a eigen, nothing but a eigenvector of a, okay. When we will include the zero vector with it, you will get the one vector subspace of V, okay. Is it fine? Why this is a non-empty? Could you please tell me? Why is a non-empty?
Because
Yeah, please tell.
if it will be empty,
Sorry.
then the subspace will have zero.
Hmm?
No, so that's what.
Please tell. Sorry.
No, so I gone the wrong direction.
Yeah. So now when we are starting with eigenvalue, eigenvector, na, so already this u is a v is a eigenvector corresponding your lambda, okay. So that time at least v will be there, okay, and multiple of all v will be also in this set. Here previously we observed already this, if u is an eigenvector of a, then u generated by, okay, sorry, this subspace generated by u is also eigenvector of a, okay. If u is an eigenvector of a, then any multiple of u is an also an eigenvector a. This is the meaning of these sets, okay. We are collecting all, okay, all vectors such that x equal to lambda x, and this will form a vector subspace of V, okay, for any lambda R. If lambda is an, if lambda is a not a eigenvalue, that time also it will form a subspace, because if lambda is a not an eigenvalue, we will get only x is a 0, okay. If lambda is an eigenvalue, then we done, because if lambda is an eigenvalue, that time here we observe that this is a subspace, okay, we already know, then we done. If lambda is not an eigenvalue, okay, then v lambda will be only 0 vector, okay. That time also we will get this is a non-empty subspace of B. Is it fine? Please tell me, is it fine or not? Is it fine for everyone? Robi?
Yes, sir. Getting.
Little, what is the confusions?
No, sir. Getting, sir. I
Okay,
got
okay.
it.
Rajesh?
Yes, sir.
Okay, them done. So previously I asked one question, okay. What is our aim? Why we are interested on eigenvalue, eigenvector in terms of mathematics? So there is many real life application is there, but I'm not going to in that directions. So we are mathematicians, okay. So for us, what is the needed of eigenvalue and eigenvector, okay. Please tell. Suppose I am giving to one matrix or one transformation, whatever you can take, or T or A, not issue. Okay, I am taking A only. Okay, because T and A both are equivalent. Okay, if you have one linear transformation, we will get corresponding to unique matrix. If you have one matrix, we will get a corresponding unique transformations. Okay, so what is the needed of eigenvalue eigenvector? Suppose we have one matrix A. Okay, we have one matrix A, n cross n matrix. The handling this matrix is too difficult sometimes. So if we can find a simpler form of that matrix, that the all property of matrix will preserve by that matrix, then it will be easy for us, is it or not? Suppose you have one matrix, n cross, order is n. Okay, so if we get some simpler form of A such that all property of that matrix will preserve by that matrix. Suppose there is one matrix D, simpler form of A. Okay, and all property of A is preserved by D, this D, but these two matrix don't same, because already we are taking one complicated matrix. Okay, so we need the one simpler form of A such that all property of A will preserve by this D. Then it will be easy for us to work, is it or not?
Yes, sir.
Understood my point, Vishal? Ravi, understood?
Yes, sir.
This is our main aim. We want to find a simpler form of A such that all property of A will preserve by the simpler matrix form. Okay, is it? Ans, could you understand?
Yes, sir.
Okay, this is our basic aim. Okay, so here I am writing. Okay, what is the central problem for us? Okay, we can central problem. So we have one complicated matrix. We want to find one simpler form of A such that all property of A will preserve by this matrix. Then how we will get this matrix D? This is our aim. Okay, this is our simpler, this is our central problem. Okay, what is our central problem? Central problem is to find, okay, whether there is a basis, okay, vi of v consisting of eigenvectors of A. Okay, okay, so why this is the central problem for us? Previously I told us our aim is to find a simpler form of A, and right now I am writing this is our central problem, to find the basis vi of V such that this all vi is the eigenvector of A. So what is the relation between that? That find a simpler form of A and find a basis of V consisting of eigenvector of A. Means we will find a basis of V such that all the basis vector are eigenvector of A. What is the relationship between these two statements? My first statement is find simpler form of A, and second statement is find whether there is a basis Vi of V consisting of eigenvectors of A. What is the relationship between these two statements? Okay, so will we have that if this simpler form will take, this is the only diagonal matrix. This is it interesting or not? One matrix, we have one matrix, from there we are getting a diagonal matrix that all properties preserved by that matrix. Okay, and if you take this a diagonal matrix and there is a directly connection with this statement. Okay, suppose one matrix is similar, or suppose D is a simpler form of A and D is a diagonal matrix, then there is a directly connection with this statement to find whether there is a basis Vi of V consisting eigenvectors of A. Okay, there is a directly directly connection with these two statement. So if someone can find the basis of V consisting the eigenvector of A, that means we done. Means A have one simpler form. What is the simpler form? Simpler form is nothing but a diagonal matrix. So we can, if diagonal matrix, if everyone are familiar with diagonal matrix, please tell me.
Yes, sir.
Diagonal matrix is nothing but only diagonal entry will be there. Suppose lambda 1 0 0, okay, 0 lambda 2 0, okay, only diagonal will maybe non-zero or might be zero, no issue, but rest of the of diagonal entries should be zero. So one matrix is looks like your this one. Is it not a miracle? So all property will be preserved by only this matrix. Okay, but not every matrix is for every matrix we can't get this type of matrix that such that every property of A will be preserved by this D. But if we can find the basis, okay, of V such that all basis vector is the eigenvector of A, that time we will get uh, this type of D, means A is similar to D, one diagonal matrix. Those matrix is called as diagonalizable matrix. Okay, understood? And that time this eigenvector is called as eigenbasis of V. Okay, understood or not? Please tell me. Means I am writing again. Okay, so we call such basis and a eigenbasis, or simply we can, if there is no confusion, so simply we can tell the eigenbasis. Okay, eigenbasis of V. Okay, so if we get the eigenbasis of a matrix, sorry, eigenbasis of V corresponding to a matrix A, that time A is nothing but a similar to a diagonal matrix. Okay, that time we will say this is a diagonalizable matrix. Okay, so I am writing the definition of diagonalizable matrix. Yeah, please tell me what is the definition of diagonalizable matrix. Yeah, please tell me. What is the definition of diagonalizable matrix? Here I have mentioned two notions. In term of A is similar to a diagonal matrix. One is the find a eigenbasis, okay, of V. O- o- One of you can use one of the definition, no issue. Okay, okay. If you use this definition, it's also fine. If you have one eigenbasis of V, then we can write A is an diagonal. A is similar to a diagonal matrix. If you write that A is similar to diagonal matrix, then we will get this one. So whatever you want, you can write as a definition. Okay. So please give me one example of a diagonalizable matrix. Please give me one example of a diagonalizable matrix. If someone take yeah, zero matrix, or someone take this one, 1 2 0 0. This is already, yeah, identity matrix also. It is already in diagonal form. Okay, diagonalizable form. It's already in. But except this one, can you give me one such example? So if you take this one, take 1 1 1 1. Okay, you can find check it in home that this is also one a diagonalizable matrix. Okay, so I have one question. Okay, so this is our central notion, central problem to find the eigenbasis of V. So can you give me one necessary conditions for that? So when we will get when we will get always a eigenbasis of V, one necessary condition. Can you give me?
Sir, determinant non-zero.
If determinant non-zero, then will every time it will be diagonalizable. You are saying it's not. Please try to think in connection of this one. So our aim is find to a eigenbasis. Okay. So please assume, suppose you have one matrix A and all eigenvalue, okay, are distant. Okay. So we have one matrix, okay, cos corresponding to matrix, all eigenvalue are distant. Okay. Then corresponding this one you will get one Vi, corresponding this one will get Vj. Okay. So all Vi, Vj also not equal. If these two are equal, then this have to be equal. Okay, you can verify this one. So if you have one matrix such that all eigenvalue are distinct, then we will get the distinct one minute, then we'll get distinct eigenvector. Okay, not only distinct, this not equal to this one also. Suppose this equal to this one, then we'll get these two equal. Is it or not? Please tell me. If your lambda I not equal to lambda j, then Vi is eigenvector of lambda I, Vj eigenvector of lambda j. That time we'll get Vi is not can't be multiple of Vj. Are you agree with me? Are you agree? Please tell me yes or not. Are you agree with me? If lambda not equal to lambda j, then yeah, suppose your lambda is not equal to lambda j, where lambda j lambda I lambda j are eigenvalues of A. Claim is okay. Vi is the eigenvector of this one, corresponding eigenvector. Okay, not equal to alpha into Vj. This is a corresponding eigenvector of lambda j. This is my claim for all alpha belongs to R. Are you agree with me? Yeah, here I have mentioned one. This one. Suppose your V is an U is an eigenvector of A. Then any vector multiple of U is an also eigenvector of A corresponding the same eigenvalue. Okay, lambda. Okay, so here so if this is a multiple of this one, suppose this Vi is a multiple of Vj, that time we will get that Vj is also eigenvector corresponding lambda I. Then this is the, and that time lambda I should be equal to lambda j, so that will be the contradictions. Okay, if Vi equal to alpha times Vj, that time it's forced to lambda equal to lambda j. Okay, understood or not? Please tell me. Understood? Why this is not equal? Please respond. Understood or not?
Yes, sir.
Robi?
Yes, sir. Got it.
Hans?
Yes, sir, fine.
Okay, so from here what we are getting? We are getting V1, V2 up to Vn. Suppose n is the order of A. Okay, so this is are linearly independent. Yes, Vishal is correct. If they are equal, then they will lie on the same eigenspace. Okay, so that time lambda I, lambda 2 have to force to equal. Okay, so this where we are getting the linearly independent, okay, sets. Are you agree with me? Suppose
Yes, sir.
lambda I is not equal to lambda j, that time we are getting v1 up to vn is are the linearly independent sets, all are eigenvector of A. Is it fine?
Yes, sir.
Yeah, so this is the linearly independent sets. There are total n vectors are there, and this is your matrix A or linear transformation. So domain is dimension n. Okay, so this will form a basis of V. Are you agree with me? The dimension of the domain is n. Okay, and we are getting one linearly independent sets of n vectors. Then this forced to be a basis of V. Okay, so clearly V1 V2 up to Va be a basis of V. Are you agree?
Yes, sir.
Yeah, so this is the necessary condition. Suppose one matrix A has all eigenvalue are distant, then A has, this is your eigenbasis of V, then A has a eigenbasis, okay, or sorry, uh, corresponding the domain of A, V has a eigenbasis, okay. That time A is similar to a diagonal matrix. This is the one condition. There are many other condition is there. I am not going to that details. You can read through books. This is the main aim, okay. So previously I mentioned that eigenvalue may not be exist. So I am going to, I am coming to that one. So yeah, take this one, okay. One matrix, take one transformation T such that in R2, take transformation E1 is, we are familiar with this transformation. E1 is goes to E2 and E2 is goes to 0. So if you get the, what will be the matrix will looks like this one, okay. If you find the matrix of this one, we will get this one. Is it or not? You can find that matrix of it. So now try to think, okay. Suppose take one non-zero vector from here, u, okay, u equal to xy. Is it fine? If this is your transformation, we will get a is this one. Is it fine or not? Please tell me. This is your linear transformation. I am claiming that corresponding this transformation A is that this one. You can check very easily, because if you take E1 we will get E2, E1 E2 equal to 0. You can check it. So this is satisfy that if you, when we are act A on basis E1 we will get E2, and act A on E2 will get 0. So this T and A must have to same. Or you can find how what is the procedure. You can follow the procedure also, or you can. So is it fine that A is a matrix dependence of T? Please tell me, is it fine or not? Okay. Or you can find in home, no issue. So my claim is A has no eigenvalue. How we can prove it? So take a non-zero vector here, u is non-zero, okay. Take, this is your non-zero vector, okay, from R2, okay. So what will get when it will act on you, will get 0 0 1 0, okay, xy. What will get? Will get 0, sorry, 0x. Is it?
Yes, sir.
Yeah. So this must to be have this form lambda into xy, okay.
Yes, sir.
Okay, now 1 minute, I have to mention properly, okay. It has Yeah, it's fine, no issue. 1 0. Okay, then what we'll get? We are getting that 0 into x, okay, equal to lambda into xy. So what we'll get here? We'll get we are getting that lambda into x equal to 0, okay, and lambda into y equal to x, okay. Two possibilities there. What possibility? Lambda may be 0 or not. Two possibility. First case, if your lambda is 0, okay, and second case, if lambda is non-zero, okay. Suppose if your lambda equal to 0, then what will get? That time what will get? Please tell me. If your lambda
X
equal to
is
0,
0.
then what will get? X equal to 0, okay. Is it fine or not?
Yes, sir.
Okay, so okay, then what will get the contradiction? Will get 0 and y. Yeah, 0 is the eigenvalue of a. Then it will not work. Yeah, corresponding this one 0 is an eigenvalue of a. Okay, so this example is will be not be work. A has the eigenvalue. Okay, is it or not? Yeah, basically both eigenvalue are 0 here. So my example is wrong. A has the here A has the eigenvalue. So I have to think about another example. Okay, I could not check it. So if a lambda is 0, both lambda is here, both eigenvalue are 0. So I have to construct. I have to think about another example. I am correct or not? I think two eigenvalue are 0. Is it? Are you agreeing with me? Has a two eigenvalue are
Yes, sir.
yeah. So it will be work. I am going to another example. Okay, take this one. Take 0 0 1 minus 1, this one. Okay, yeah, I think it will be work. And I little bit I did mistake. This is an example of a not diagonalizable matrix. Okay, here eigenvalue exists, but you can check that this is a not diagonalizable matrix. Not diagonalizable matrix means you will not get a basis of R2 such that the basis vector contains the eigenvector of A. Okay, so yeah, this so I am proving that one first. Then I will go that this is a matrix such that its eigenvalues not exist. Okay, in R basically eigenvalue not exist in R. Not exist in R. If we think about this is a real matrix, then its eigenvalue is not exist. If you think about complex matrix, that time eigenvalue will be exist. So you can check it. I want to prove this one is that this one is not an diagonalizable matrix. Okay, how we can prove? So here we are observing that both we are getting both eigenvalue is 0. So corresponding the, if lambda is a 0, not if when lambda equal to 0, okay, is an eigenvalue of a equal to, yes, you can tell, yeah, Vishal is correct, is non-zero nilpotent matrix. Okay, and you can check with your definition. Suppose lambda equal to 0 is an eigenvalue of a, that time we can find the eigenvector. What is the eigenvector? This one only. And both eigenvalue of a at 0. Okay, both eigenvalue of a and 0, and we are getting that 0 into x, where x is non-zero, belongs to R, is a eigenspace. Okay, and both corresponding eigenvalue 0, this is your eigenspace, and this is only one dimensional. So this one can't be basis of R2. Okay, this one can't be, only this one is there, na, take this one. So we need another, for basis of R2 is 2, so we need two linearly independent eigenvector, but eigenvalue of a both are 0, so we are getting only one. So what is the others we are not getting. Okay, so from this matrix we are not getting the eigenbasis of R2. Okay, so this is not a diagonal matrix. So A is not a diagonalizable matrix. Understood?
Yes, sir.
Yeah. So rest of the things you can read from books. Okay, I will suggest to read from books, and you can check that there is no eigenvalue of this matrix in R2. Okay, so I think everyone are familiar with the characteristic polynomial. Okay, so you can read all those things. If you read all those things, and next class I will teach about inner product. Okay, please tell me what is your suggestions. If you want, I can continue with these things. Okay, if you don't want, if you want a little bit about inner product, then I want to go for inner product, or I can continue this one. Whatever you want, please tell me. If you want, I can continue this session in next, because next is last. So whatever you want, I will teach you. Previous year,
Sir,
yeah, please tell.
सर इसको कंप्लीट कर देते हैं सर पहले.
This one.
Yes,
Okay,
sir.
then I'll continue, because sometime categorize some matrix, we need the inner product sometime. So if needs, I will tell little bit about inner product, then I'll go, because inner product is a generalizations of angle. Okay, so
Okay, sir.
you should read all those things. Okay, you need Vishal need the last year question paper, so I have to ask to NPTEL team. Okay, then I will tell you in my next class. Okay, right now I don't have the last year question paper. Okay, so do you have any questions? So then I can stop here.